In this video, I will begin talking about our next functional group, which is the ether. So the ether is just an oxygen that is sort of sandwiched between two carbons like this. And so that's what we will be looking at in this video. And we'll talk a bit about some of the physical properties and the nomenclature of ethers. So the thing to notice first in comparison to some other similar oxygen-containing functional groups, the ether does not have any hydrogen bonding. So if we look at our water here and our alcohol, we have these hydrogens that can hydrogen bond with other molecules. When we have the ether, we do not have that. So with water, we have hydrogen bonding. With alcohols, we have hydrogen bonding. We do not have any hydrogen bonding in our ethers. And so that makes a pretty big difference when it comes to the boiling point. So water has a boiling point of 100 and ethanol of 78. Then we get down to dimethyl ether, and that is negative 25 degrees Celsius, which is a lot closer to propane, which is the alkane of similar molecular weight. So it's very close in molecular weight to the propane. And we can do the same thing with the diethyl ether. So we see that this is a lot more similar in boiling point to the pentane rather than the N-butanol, which is a similar molecular weight to the diethyl ether and the pentane. So losing out on those hydrogen bonds has a large effect on the boiling point for ethers. And so ethers are often used as organic solvents. So some popular ones are the diethyl ether that's used a lot in organic chemistry. We also have the 1,2-dimethoxyethane or DME and tetrahydrofuran, and you sometimes see 1,4-dioxane. So I personally have used all three of these before. I've never used the 1,4-dioxane. And so ethers are nice because they can dissolve both polar and nonpolar compounds, and they are unreactive towards strong bases. So in this table, I have compiled some solubilities for diethyl ether and for water, so we can compare these. So the first thing to notice is that water is slightly soluble in diethyl ether, and diethyl ether is slightly soluble in water. And that's why if you are in the lab, you usually want to use some kind of drying agent when you're doing like a separation using water and diethyl ether, because you will end up with some water in your diethyl ether. Then we see that hexane is miscible in diethyl ether. Miscible just meaning that you can mix it in any proportion and it will completely mix, where hexane is immiscible in water, which means that in any proportion it will not actually mix. It will completely separate. And so that's showing some of the non-polar character of diethyl ether. And same with hexanol, that's miscible in diethyl ether and is only very slightly soluble in water. And then when we get to these alcohols here like isopropanol, ethanol, and methanol, we see that these are miscible in both diethyl ether and water. So those are polar protic solvents, and they are miscible in diethyl ether, even though diethyl ether is oftentimes thought of as an organic or nonpolar solvent. And acetone too is miscible in both diethyl ether and water. Then we see dichloromethane and ethyl acetate, which are nonpolar solvents, are miscible in diethyl ether, but they are only very slightly soluble in water. And then benzoic acid, we see that this is soluble in diethyl ether, as is phenol, where again, these are only slightly soluble in water. Aniline, soluble in diethyl ether, only slightly soluble in water. Then DMSO is immiscible in diethyl ether, but it is quite soluble in water. Sodium chloride is immiscible in diethyl ether, but it's very soluble in water. But if we have something like lithium bromide, which is a very small cation with a very large anion, we can start seeing solubility in ether. And you'll also notice that it's even more soluble in water than sodium chloride is in water. That's because having those large differences in the sizes of the ions make them easier to break apart. And so we can compare some of these different ethers here. So we have the dimethyl ether, the ethyl methyl ether, the diethyl ether, dipropyl ether, and diisopropyl ether. So we see that these are increasing in boiling point, so negative 25 to 8 to 35 to 91. The diisopropyl ether is going down in boiling point. That's because it's more branched, it's less linear, and so they don't stack together as nicely. And then we see the difference between furan and tetrahydrofuran. We are seeing an increase in the boiling point there. And the other thing to notice is that the pKb, so the alkalinity of our diethyl ether, which is a popular solvent, is about the same as ethanol and water. So water is a little bit more basic than the other two, but they are all kind of within the same ballpark. And so we're talking about the alkalinity, the basicity of that oxygen right there. So we add our acid and we protonate that. So those are going to be pretty difficult to protonate. So another important type of ether are what are called the crown ethers because they kind of look like a crown. And so these can complex metal cations in the center of a ring. And so the size of these rings determines which cation it can solvate. And so complexation by crown ethers can allow polar inorganic salts to dissolve in nonpolar organic solvents. So if we have the small one, we can dissolve lithium into it. This somewhat bigger one, we can do sodium. Even bigger one, we can do potassium here. And this is just a common way of showing these crown ethers like this. So we see that the oxygens on here are what are coordinating with that cation in the center. And of course, when we go to a new functional group, we have to learn some new nomenclature. So for ethers, what we do is have the more complex alkyl group as the root name, and then the rest of the ether as an alkoxy group. So we treat the smaller version as sort of a substituent on the larger chain. So for instance, what we often call ethyl methyl ether would actually be called methoxyethane. So this is our methoxy group right here. This is our ethane right here. So methoxyethane. Similarly, we have the benzene ring right here, then this methoxy group, so methoxybenzene. Over here, we have the chloromethoxy, so this is our chloromethoxy right here, and then methane, so chloromethoxymethane there. Somewhat more complicated, we have this 3-ethoxy, so this is our ethoxy group right here, then 1,1-dimethyl cyclohexane. So the rest of this is our 1,1-dimethyl cyclohexane. Then we have ethoxyethane, so this is our ethoxy group. This is ethane right here. Of course, we usually just call this diethyl ether, but its IUPAC name would be ethoxyethane. Then 2-ethoxyethanol right here. So we have our ethanol right here, then we put this ethoxy group on it. And so this carbon right here is counted as the one carbon, so that's why it's 2-ethoxyethanol. Then we also have epoxides, which are an important type of ether. And so the term epoxy is used as a substituent, naming the numbers of the two carbons involved. So for instance, right here, we have 1,2-epoxyethane. So this right here is our ethane. And so the epoxy group, which is this oxygen right here, is on the 1 and 2 carbon of it. So another way that these are often named is using this word oxirane. So this one could be called ethylene oxide or oxirane. And so then the next one right here, we have 2,3-epoxy pentane. So this is our one carbon, 2, 3, 4, 5. So it's a pentane, and the epoxide is on the 2 and 3 carbon right there. So that means 2,3-epoxy pentane, or 2-ethyl-3-methyl-oxirane. This one over here, a little bit more complicated. So we have 2 methyl groups right here, but we can count one as being part of the backbone. So we have 1, 2, 3, 4, 5, 6. So this is a hexane right here. And so we call it 3,4-epoxy. So this is a 3 and the 4 carbon right there. Then the 4-ethyl, this ethyl group coming off that 4th carbon. 2-methoxy, so this is our 2nd carbon. One of these methyl groups are coming off of it. So 3,4-epoxy, 4-ethyl, 2-methyl-hexane. Then down here we have trans 1,2-epoxy 4-methylcyclohexane. So the trans is talking about the epoxide group here with respect to this methyl group right there. So it's the 1,2-epoxy, which is our epoxide here, then the 4-methyl, which are trans to each other. So trans 1,2-epoxy 4-methylcyclohexane. Then over here we have cis 2,3-epoxy 4-methoxy hexane. So this is our methoxy group right here. We have 1, 2, 3, 4, 5, and 6 carbons on there. And this comes off the 2, 3 carbon right there. Then we have this methoxy group right here. And we're saying that that is cis to the epoxy group. So cis 2,3-epoxy 4-methoxy hexane. Then we have the nomenclature of the furans, pyrans, and dioxanes. So furans are just molecules that look like this right here. And so when we put a substituent on it, we can call this 3-methoxyfuran. So this is our methoxy group right here. We're counting from here, 2 and 3. So 1, 2, 3. So 3-methoxyfuran. When we get rid of those double bonds, we're adding 4 hydrogens to it. So we call it tetrahydrofuran, or THF. Then the puran, so again, we have the 2 double bonds like this, and we can put substituents on it. So this methyl is on the 1, 2, 3, and 4 right there. So it is 4-methylpuran. And if we put 4 hydrogens on it to get rid of those double bonds, we call it tetrahydropuran, or THP. Then the dioxanes here, so we can have 1,4-dioxane and 1,3-dioxane. There is a 1,2-dioxane, but that is like a peroxide, and so it's not used that often. And so we can then put substituents on here as well. So we have 3-methyl 1,4-dioxane. So we have 1, 2, 3, and so we have the methyl group on the third one, so 3-methyl 1,4-dioxane. Over here we can go like this, so 1, 2, 3, 4. So we have 4-methyl 1,3-dioxane. So we can see here that this is on the 1 position and the 4 position. That's the 1 position and the 3 position. So that's where those names come from. And similar to the ethers, we have thioethers, or sulfides. And these are just the same thing, but with a sulfur instead of an oxygen. And so we can have something like methyl thioethane. So this would be like the methyl ethyl sulfide, so similar to the methyl ethyl ether. Then we could have this right here, so methyl thiobenzene, which would be like the methyl phenyl sulfide. And so that would be like having the methoxide on our benzene if we were looking at this as an ether. And so the last thing we can look at here, so we can first look at the mass spectrometry of ethers. We can get essentially 2 types of cleavages that are going to be common for ethers. So we can get a splitting right here, so 1 carbon away from the oxygen or right at the oxygen. And we call this one the alpha cleavage and this one the loss of an alkyl group. And so both of these make an oxonium ion. And we can actually have both of these happen as well. We can see an alpha cleavage here on our diethyl ether, so we lose 15, and so this would be an M over Z of 59. The loss of the ethyl group will now be a loss of 29, and so we get an M over Z of 45. And if we have both of those occur, so if we just take this one right here and sort of bring it down over to here, then do a loss of an ethylene right here, then we would get this M over Z of 31 right here. Finally, the NMR of ethers. So for the carbon-13 NMR, we will get peaks between 65 and 90. For HNMR, it will be between 3.5 and 4. So having these peaks in the NMR could be seen either with an alcohol or an ether. So these are not going to be conclusive for ethers. So you would need an IR spectrum to determine whether it's an alcohol or an ether. So the alcohols show up really well in the IR spectrum. They have a very characteristic peak at the 3300 range, and so that would tell you whether you have an alcohol or an ether. But anyway, that was everything I wanted to talk about in this video. I hope you found that useful, and I will see you in the next one.